I'm Luke. I was at Twitch for like 9 years until very recently. Volunteered for the layoffs. So now I'm just doing mock in my free time for a little bit, doing some open source work and really trying to prove out this idea that I started and see it at least to some finish line and try to get a standard going. So what's wrong? Why am I here? Like, why am I spending my energy on this? Why aren't I just playing video games during my time off? Well, really it comes down to the live streaming ecosystem. So if you want to do real time, like conferencing, use WebRTC, naturally. But if you want higher quality and higher latency, you just have to look somewhere else. For contribution, you usually look towards RTMP and SRT. And if you want to distribute to a lot of people, you look towards HLS- or something similar. And the big question is why? Why do we have these three very separate use cases? Under the hood, the media encoding is the same. Almost exactly the same for all of them. But what really changes is how we send media over the network. So really want to say, like, why does this simple encoding, this just I frame, B frame, P frame, how do we send this over the network, and why does it matter? Is where I want to start with. So the little thing I'm calling latency theory is, what does a protocol do when there's congestion? If there's perfect network conditions, you can send everything. You can send IPPP in the order it was created, and it will arrive on the other side. There's no issues. But what happens if there is an issue? What happens if there's packet loss or buffer bloat or some stall over the network? And that's what really differentiates all these protocols. They all do media the same way. They just make different decisions on what to do during congestion. So simplest is RTMP. We send everything over a single TCP stream. It's all one ordered snake. And if there's congestion and there's, the network bitrate is lower, we can lower the encoder's bitrate, and that, as a way of backing off a little bit. But fundamentally, everything that we already committed to TCP is still in that queue. It's either sitting in a TCP socket, it's sitting in the application, sometimes even on routers, that's buffer bloat. And this is latency. This is kind of the problem, where the latency can just grow unbounded as you have more and more frames that depend on each other. So with HLS-, it's similar. If there's congestion, we can't just change the encoder's bitrate, but we switch down to a lower rendition. That's the congestion response. But similar, we still have this backlog of the previous segment we need to get through before we can start downloading the next one. And you could try to close the previous request for the previous segment. It just gets messy, and it's very hard to even tell that you're supposed to do that. So you still kind of have this fundamental head-of-line blocking issue. So that's why some other protocols, like WebRTC and SRT, go a different direction. If head-of-line blocking is the issue, then UDP is the answer, because you can just send whatever packets you want. And the idea is, if there's congestion, I can just choose not to resend these packets or not to send them in the first place. So you take the frames and divvy them up to, I think I calculated like 5,000 packets a second, or UDP packets a second, for 6 megabits a second. How they usually work is you have a kind of a deadline. You choose how much latency you're willing to accept, and you drop anything older than that. So WebRTC is more or less hard-coded to like 300 milliseconds. Otherwise, if you want more than that, the browser usually won't let you. And SRT, you negotiate the latency up front. You negotiate this fixed deadline, at which point you just won't send packets anymore. The problem is, especially for a CDN, it's hard to know what packet to send next or which packets to drop. You have, again, 5,000 packets a second, and they don't really have any information about them. If I blindly drop them, I'm no better than a router, really, that just does random packet loss. And if I try to be smart, I have to try and decode media fragments in these packets. and that's just expensive. And that's why you really don't see too many WebRTC or SRT CDNs. It's too media specific. So why are we doing something new? There's 14 existing standards out there, and we're trying to make a 15th one. And maybe this is just going to be the 15th standard. But the goal is that there's some good news. TCP's dead. Don't use TCP anymore. It's dead. So TCP is replaced by Quick, and that's what this whole session is about. It's IETF RFC 9000. It was recently standardized. Was designed for HTTP3, but it can be used as a generic transport as well. Has far more features, too many to cover, and also it's far more complicated as a result. Here's a quick rundown. I don't want to spend too much time on this because there's going to be other presentations that cover these too, but everything's fully encrypted. Even sequence numbers are protected to try and hide them from routers. There's a fast handshake, one round trip. You establish the connection, fantastic. Roaming support, I like this one. You can switch between Wi-Fi and cellular and the connection doesn't drop. It's like, how did it take this long to implement that? There's better congestion control. This is a big deal if you're doing like broadcasting from Windows and the TCP stack is just kind of poor. And you can do better than BBR. In fact, we haven't really begun to explore that realm. And there's some really cool load balancing stuff you can do. That's more secret stuff. You can do some really neat things with Anycast or just stateless load balancing. It's going to be, I'm looking forward to that space the most, but that's kind of me nerding out about server-side stuff. But what does the API, what does Quick actually offer as to the application? So it offers multiple independent streams. You can think of these like TCP streams, but they all share a connection. You can create them with no cost. Either side can create them. And you can close them after a certain amount of time with a fixed length, with an error code. And they just kind of, they're actually independent of each other. The way that HTTP3 works is each request is a separate stream. So the requests don't collide with each other, and then you just write back the response in the same stream. So we can use this API to our advantage. We can try to figure out a way to send media over it. And now there's a bunch of different ways to try and send media over Quick. So at Twitch, I developed Warp. I was working on fixing distribution. Effectively, we're using something similar to LL Dash, and we kind of hit a latency bottleneck where we just couldn't get it any lower without impacting quality. So I made Warp. Meta came along, and for ingest, they're having issues with RTMP. So they made Rush, like a layer on top of Quick. And then Cisco also released QuickR, which is effectively, they're doing conferencing. So they're trying to solve the CDN and conferencing issue. And all of these drafts are eerily similar. That was a reason, like that was the sign we should make a working group. We should try to standardize this, merge all the drafts together, and then all of a sudden, like, we can do all three of these at once with minimal changes. So I'm biased. I made Warp, so I'm going to cover it a little bit. And it's a little easier. But effectively, you have 2 streams in this example. Each stream is just a segment. It's a GOP. Audio and video is separate streams. And the idea is you just write the video data. In this case, it's CMAF, which is really nice. And you have a little header that you write at the start that gives the relay or the CDN instructions on what to do during congestion. And the instructions are, it's just a priority queue. It says, like, this is the most important one, then this is the second most important one, then this is the third most important one. So when a relay or anything in the whole video system encounters congestion, it just follows these instructions. And it doesn't even realize there's media inside these streams. What happens there is then a player may decide, hey, I don't want to wait for these streams. They're being starved. And it will decide to drop the frames. So this is up to the receiver to decide when to move on. And the relay just kind of blindly keeps sending in this priority order. So what this really means is that, A, CDN support is, like this is designed for CDN support. It's meant to be really simple instructions. It's meant to make it so the CDNs can't screw up. Like these aren't hints. These are very explicit. If there's congestion, send this first. My favorite feature is viewer's choice, as opposed to WebRTC or SRT that are very fixated on it must be this latency. The idea is the player chooses how long to wait. It's the buffer size. So you can have somebody who wants real-time latency on fiber in the US and somebody who just wants to sit back on the couch and watch from their TV on cellular in India or something. And you can use the same CDN, the same pipeline, the same software, and the only difference is how long those players wait before they move on, before they decide to drop the frame. And what this looks like is audio continues because it's higher priority, but video will just freeze and then skip forward. You've seen this if you've done any conferencing solution. Web support. So Quick has web transport. It's pretty much the equivalent to WebSocket. You get quick access in the browser. There's also H3 is another way you can get web support, but we're doing web transport. And like I mentioned, we're solving the gambit of contribution, distribution, and real-time latency. We're trying to, it's always ambitious to try and unify these very disjoint protocols, but it actually seems like it will work. You can get involved. There's a mock working group. There's meetings for IETF. There's a mailing list. There's people like me come up on stage and present. There's a draft we're working on. It's currently in my repo, but eventually when we get it to a good enough place, we're going to ask for adoption. So it's an official IETF draft. It's not a standard. It's got years before it will be a standard. Don't worry about it. And then in my free time, I'm working on the demo. So I have this demo code base. It's Go and MSE, but because I'm no longer employed, I get to have fun, and I'm doing web codecs and Rust. So it's not quite ready to show off yet. But my plan is to make public demos, make blog posts, really evangelize it. And I guess you can watch me live doing this if you want. I don't know why I put that. There are many ways of doing Quick. And I just want to say that this media over Quick is one possible way. We're focusing on delegating as much as possible to Quick layer and having a thin media layer on top. In fact, for CDN support, we don't even want the CDN to know it's media. That's one of the explicit goals. We only want the encoder and the decoder to know it's media, and everybody else in between does not know or care. There's other ways. RTP over Quick is another IETF effort where you're just trying to take RTP and put it over Quick datagrams. Of course, you can use HLS- over H3, and there's an upcoming talk about that. That's pretty cool. And of course, there's also SRT over Quick, where Quick has an optional datagrams mode, which effectively is just a UDP replacement. It's more complicated than that, but you can take your favorite protocol, send over Quick, get most of the benefits, and that's often good enough. So, yeah, we got some upcoming talks. Thank you so much, and feel free to, if you see me in the hallway, grab me, tell me why this won't work, and I'll tell you why it will.